So up to this point, we've been talking about ideal oscillations. I have here open the FET tutorial again, and I have it set to no damping. So I know if I pull the mass down and let it go, the oscillations will continue forever. If there realistically is no damping at all, there's nothing to take energy out of the system. Which, if we look at the energy graph on the left, we can see that total amount of energy is not changing at all. Of course, we're going from potential to kinetic, but the total energy doesn't change. Now, over here on the right, I'm going to move damping up just a little bit. Sorry. And notice the mass now, its oscillations are decreasing with time. So it's not moving up and down nearly as far. On the left, we can see that kinetic energy bar graph has significantly decreased to nearly zero because this mass has essentially almost come to rest. So when there is damping, we end up with some of that original mechanical energy turning into thermal energy. And that's what I want to talk about now, is this concept of damped oscillations. There's many ways in which our oscillating systems can be damped. It could be in terms of air resistance or drag. It could be friction of some sort. There's a variety of ways that systems can be damped. As far as the equations we are going to use, we're going to talk about drag. In a system where the objects are not moving very fast, the drag force is actually linearly related to the velocity. So this is our drag force. The negative sign indicates that the force is opposite the motion, opposite the velocity specifically. So if I had that mass on the spring oscillating up and down, if its motion, if its velocity was down, then that drag force would point upwards. And so this drag force is always working to take energy out of the system. It's always opposing the motion. B here is called the damping constant. This is unique to the system itself and how the system is being damped. And then V is the velocity. Now, this damping constant needs to have units, because if we think about the force has units of newtons, which we know also is a kilogram times meters per second squared. B and V, we know V has units, meters per second. So B has to have some sort of units such that when we multiply it by meters per second, we end up with a Newton. So B has units of kilograms per second. All right, when we talk about this concept of drag and this specific way of damping, if we think about when we talked about a mass on a horizontal surface connected to a spring. In the ideal situation, we know if we pull the mass to the right and release it, it ends up oscillating back and forth, left and right, and it would do so with the same amplitude indefinitely. Now, that's the ideal situation. Realistically, not only do we have the spring that's always causing the motion, the spring force we write as a negative kx, x representing how far the spring is stretched or compressed. But if we're also going to account for this drag force, the net force in the x direction will be the force from the spring, the force of drag, and that net force has to equal mass times acceleration in the x direction. In the ideal situation, B would be 0, meaning no damping, and then that's where we had the relationship of this spring force causing the acceleration, but we know acceleration is the second derivative of the position as a function of time. And this is where our generic equation came from for the ideal situation. I guess I need to account for that initial phase shift. And we also found that omega is equal to the square root of k over m. So k is the spring constant and the mass. Ideal, no damping, we're saying that the damping constant is 0. Now, with this damping constant and having the system being damped in this way, we now have a more involved differential equation because v, velocity, we know is the derivative of position with respect to time. Acceleration is still the second derivative of position with respect to time. So we need a function for x in here such that it satisfies these conditions where we have a term with the velocity and a term with the acceleration. Now, of course, differential equations is not a prerequisite for this course, so we're just going to give the solution. The solution to this equation to represent this damped oscillation looks like this. There's an exponential portion and a cosine portion to represent the oscillations. So in the ideal situation, if we just think of the graph, the position of our ideal oscillator as a function of time, the amplitude always stayed the same. In the case of damping, that amplitude decreases with time. So it gets smaller and smaller and smaller and smaller. So in this equation, this new equation for position as a function of time, we have this portion, A naught represents the initial amplitude. So up here. This A naught exponential port, e to the negative bt over 2m, represents how the amplitude, this amplitude is decreasing with time. So we can draw kind of a dotted line here that connects those peaks together. And this portion, this amplitude, is changing or decreasing exponentially. How steep that exponential part is depends upon that damping constant. The larger B is, the larger the damping constant, the faster that exponential will decay down. The cosine portion is then allowing us, so the whole thing together with the cosine allows us to say exactly where the mass would be at a specific point in time. So we could come over here at this time, this is where the mass would be. So that equation as a whole tells us where our oscillating object, the mass itself, is at any given moment in time. The first portion just tells us how the amplitude specifically is changing with time. Now notice in this cosine portion, we have this omega prime. All that means is the damped angular frequency. the rate at which the system oscillates is affected by the damping constant. So that equation looks like this. Omega naught in here is what we call the natural or resonant angular frequency. So for example, for our mass spring system, omega naught is the ideal. So what omega would be in the ideal situation. So omega naught would be the square root of k over m. But having damping affects the overall rate at which the system will oscillate. And so we end up with this second term in here. It is completely possible to have B be large enough that omega prime goes to 0. And we call that a critically damped system. It is also possible to have B be large enough that we end up with a negative answer in there. And that is called an overdamped system. And what that means is that instead of actually oscillating, have it, and it just actually just comes and reaches equilibrium. So it actually doesn't end up oscillating at all. In our problems, we will have B values that are small enough that the oscillations do occur. Our author in the e-text itself says lightly damped, meaning omega prime is going to be greater than 0. Oscillations will occur. The amplitude will decrease with time, but the oscillations will occur for at least a short period of time. So these are the main equations we have for our system. I'll do a couple of examples as well. I do want to mention the last couple concepts that we have in this chapter as well that goes along these lines. One of them is called driven oscillations. I've also heard it as forced oscillations. Something is forcing the system to oscillate. A silly but simple example that you might be able to picture. Let's say I have a kid on a swing. I can kind of model this as a simple pendulum. The mass of the child at the bottom. I know that a child wants to swing high. So I could pull them to the side, let go, they start swinging, and to get them to swing higher and higher, I would push on them every time they were swinging away from me. So I would add energy to them in time with their motion. And when I do this, their amplitude gets bigger and bigger and bigger. This is called resonance. If we add energy somehow, or push in this case, push on the child in time with their natural frequency, the rate they're already naturally oscillating at, swinging back and forth, their amplitude increases and increases and increases. The term for that is resonance. So we get a larger amplitude as time goes on. Now, I could come up to this child And they're sitting there, and I could start pushing. So apply this force. I push, but at a really high frequency. I would make them jiggle back and forth, essentially. They would oscillate. They would not oscillate with a very high frequency. They would just be swinging back and forth a little bit to match the frequency I was applying my force at. This is what we mean in general. Both of these situations fall in the category of a driven or forced oscillation. The resulting motion is different, though. If the push I'm applying is at a frequency that does not match the natural frequency, the amplitude stays small. That amplitude being small, they jiggle back and forth, or I should say oscillate back and forth at the frequency I'm pushing them at, but they don't get to swing high, which is what a child on a swing would want. If I adjust the rate at which I am applying the force, the rate at which I am pushing them, then we can reach this situation where I apply the force at the same rate at which they are naturally swinging, and that results in them swinging higher and higher, which is what the child on the swing wants. Now, there's many situations of resonance or just even driven or forced oscillations. As far as we are concerned, we're going to focus just conceptually on what we mean by a driven or forced oscillation. And that's simply making a system oscillate by somehow putting energy in. It doesn't have to be a physical force like us pushing, but there's some sort of energy coming in. If you've ever been in your car, for example, and you're waiting at a stoplight, and another car drives up next to you with loud music and the loud bass sounds, well, you may have noticed, if you've experienced this, that your car vibrates. Like you can feel the bass, that motion of your car exterior. And that's because car 2, this loud bass, this is a form of energy. The sound energy is causing your car to vibrate or oscillate. That's a driven oscillation. The larger the response of your car would be starting to match an experience of resonance. It's not helpful in any way, but it is something we experience. Earthquake codes in building bridges and building buildings is to change the natural frequency of a bridge or a building, and thus making it different enough from the earthquake waves and minimizing the amplitude, making it not reach a resonance. So just conceptually, we can force systems to oscillate, put energy in somehow. If that energy is put in or the forces are applied at a rate at which matches the natural frequency of the system, the motion will get large. The amplitude will get large. I'm going to post a link to the Tacoma Narrows Bridge. Some of you may have already seen this. This is an example of resonance that was destructive. It's cool to watch, especially since it's happened in the past, so we don't have to experience it. But it is a good example where resonance needs to be considered. For those that go into electrical engineering, you deal with resonance as well. If we're listening to a radio, for example, the signal coming from the broadcast towers is matching the electrical circuit resonance. That may not mean anything to you yet, and that's fine. But resonance has many different applications.